and the optimum flow rates of the liquid for your gas absorption column. So again, well, you need to have your plot, you have your equilibrium line, and then this line is when you have your minimum liquid flow rate, so you have some value of the outlet composition of the gas phase. So you draw this line by starting at this point, and then it should touch the equilibrium line, and that's the limit of the operation for the minimum amount of liquid that you need. And then that slope, on that slope, you can get the minimum flow rate. And the slope for the optimum flow rate is always 1.5 times the value of the slope for the equilibrium line. So remember, the equilibrium line is y is equal to mx. So the optimum flow rate, or the slope for the optimum, the slope for the operating line at optimum flow rate is when you have the slope is 1.5 times that value of the equilibrium slope. Okay, any questions? No? Do you have any questions? Okay, do you want me to go through some of the problems? I mean, I uploaded these problems at the end of last year, so some of you have already gone through these problems because I have received some emails about it, questions about them. But do you have any questions? I mean, someone else, do you have any specific questions? I'm guessing you don't have any questions. Okay, should we go very quickly through some of these problems? Okay. So for question 1, so all of these problems are very similar to the ones we did, have already done in class. So all of them follow the same approach. Okay, so in this case, we need to design a distillation column. To obtain a distillate with this composition, 90%, and a bottom's product, this composition. And so we are given this equation, which is the vapor-liquid equilibrium relationship. As I said before, there are different ways in which you may have this vapor-liquid equilibrium data. So probably you have an equation like this, like in this case, maybe you have a table of temperature and compositions, or maybe just compositions. But somehow you need to know you have some information about the phase equilibrium. And the idea here is to use the McCabe-TL method to find the number of the number of minimum equilibrium stages for case A, and in case V, you have this value of the reflux, then was the number of theoretical plates needed to achieve the distillation. And in part C is, okay, you have some efficiency of 60% for the column, then was how many actual plates you need. So for part A, the minimum number of equilibrium stages. So I would recommend you to start, so when you start solving a problem, to always draw some kind of sketch to put all the information that you know that you have about the problem. So in this case, we have the feed, well, we have the feed composition, distillate composition, and the bottoms composition. We also have the equilibrium relationship. So the first thing to do, well, once you have done the sketch, is to draw the equilibrium curve. In this case, because we have an equation that relates y with x, so you can give values of x and calculate the corresponding values of y. Vapor phase composition. So you can use any number of, because obviously the range of x is, so x goes from 0 to 1. So that's the range for x, and also the range for y, 0 to 1. So you can, between 0 and 1, you can use any number of data points. So 10, 15, 20 data points. But I mean, for the purposes of the exam, probably 7, 8 points should be fine. In this case, so how many have we here? We'll have 8 points. So remember the range is 0 to 1, and then we have different values of x. And we have calculated the corresponding values of y using this equation. Once you have your x, y values, you can make the plot. So you make your plot of y versus x. You plot this data. Use your graph paper. Please present a nice professional plot. So even if you have the correct answer, if you don't have a proper plot, I mean, it's difficult to justify having the correct answer. So in that case, you cannot expect like to have marks or too many marks. Well, for part A, because we are dealing with the minimum number of equilibrium stages, that means that we have total reflux, in which case the operating lines are on top of the diagonal. So we can simply draw the start case, starting from the distillate, or from the bottoms if you like, but I think it's easier if you start from the distillate. So you start drawing your staircase, you draw your horizontal line, then your vertical line. Remember, it's to line to the equilibrium core, down to the reference line or operating line in this case. And this is the limit, the bottom's composition. So in this case, we have 1, 2, 3 point something, about 3.3 equilibrium stages. So the McCabe-Thiele method gives you the number of equilibrium stages, but we are considering one of the equilibrium stages to be the reboiler because you have this vapor in equilibrium with this liquid, but that's also an equilibrium stage. So we have 3.3 equilibrium stages, but in terms of plates, we have 3.3 minus 1. But in this case, the question is about finding the equilibrium number of equilibrium stages, not really the theoretical plates. Okay. So part B is, okay, if you're using a reflux of 0.8, then what's the number of theoretical stages and plates and the feed plate? Okay, so in this case about the theoretical plates and the feed plate of the column. So then you have your sketch of the distillation column, you have the information, well, you put the information that you have. And then the next step, well, obviously the next step is to again draw so what you need is to draw your or to upload your equilibrium data using the equation that we have. Again, you need to repeat these steps. You need to plot your equilibrium curve, your diagonal, and locate the distillate and bottoms composition. Have your equilibrium data, you draw your diagonal. You join the dots, that's your equilibrium curve. You have to locate the distillate composition on the diagonal, the feed composition, and also the bottoms composition. Or in this case, because we are dealing with this actual reflux, so we need to draw the operating line. Remember, one point of the operating line is this point here of the distillate composition on the diagonal. And using the equation for the operating line for the rectifying section, you can calculate the value of the intercept for this given value of the reflux. And then you know the value of the intercept and you have the other point. So if you join those points, you get the line for the rectifying section. So this is the equation for the rectifying operating line. I mean, ignore these subscripts. So the value of the intercept is given by that. Sorry. So the intercept is given by this equation. Well, this term in the rectifying operating line equation. So this point here is given by xd divided by r plus 1, because you know the value of the distillate composition and you know the value of the reflux, 0.8, then you can calculate the value of the intercept, and you draw your operating line. You also then need to draw the stripping operating line. But if you remember, well, one point of the stripping operating line is this value on the diagonal, the bottom's composition. But the other point is the intersection of the rectifying operating line and the feed line. But the feed line, it depends on or the slope of the feed line depends on the thermal composition of the feed, the thermal condition, sorry, of the feed. In this case, we have a saturated liquid mixture in the feed. And go forward. So that means that our feed line is a vertical line, a nice vertical line, straight. So then we have, so then we can draw our stripping operating line by joining those 2 points. Okay. So here is a nicer diagram. So we have our equilibrium curve, or diagonal, the points of the feed, distillate, and bottom's composition. Because it is a saturated liquid feed, this is the line for the feed. We have the value of the intercept, and we can draw the rectifying operating line. And then the stripping operating line is this. One point is here at the bottom's composition, and the other point of the stripping operating line is this intersection between the feed line and the rectifying operating line. Once we have those 2 operating lines, we can draw the staircase starting from the distillate. I mean, I prefer always to start from the distillate point. So you draw your horizontal line to the equilibrium curve, and then your vertical line to the rectifying operating line, and then back to the equilibrium, and down to the operating line, and so on. And once you are above the intersection of both operating lines, you need to switch now to the other operating line. Please remember to do that, because in some previous exams, I have seen some students, still drawing everything using the rectifying operating line, which is wrong. You always have to switch then to the other operating line. And then you simply count these points. These are the number of equilibrium stages. So, I mean, it's basically the length. So it's, well, this line, so it's 1, 2, 3, 4, 5, 6 equilibrium stages, or theoretical stages. The feed plate is the plate that is above the intersection of both operating lines. This is the intersection, so this plate is above that intersection, so this will be the feed plate. The feed plate is the third plate, counting from the top. You always have to specify counting from where, from the top or from the bottom. So we have 6 theoretical stages, minus 1, which is the reboiler. You have 5 plates. Now, part C is if you have a column with an efficiency of 0.6, in other words, 60%, then what's the number of actual plates that you need? So you divide 5 by the efficiency, so 5 plates by the efficiency, you get you need 8.3 plates, but you cannot really construct 0.3 or install 0.3 of a plate in your distillation column. So you need to build a whole plate. So basically you need to install 9 plates to achieve this separation. That is to achieve 90% concentration in the distillate and 10% of the bottoms composition. Okay, any questions? Does anyone have any questions? No? Okay, question 2. And question 2 is about flash distillation. Well, part A is a flash distillation, but part B is a batch distillation. Okay, so for question 2, part A, you have we will have a binary mixture. In our case, we are always dealing with binary mixtures, and you have the composition of one of the compounds. So this mixture enters the flash unit. And then you flash the mixture, so you get like a vapor and a liquid in equilibrium. And you have the value of the remaining liquid composition, or what is the composition of the liquid leaving the flash unit. We have to use the graphical method to find the compositions, the vapor, what the composition of the vapor, and the fraction that was, uh, split. So basically, we need to find the value of y and the value of f. As always, you need to have information about the phase equilibrium. So we have this equation in this case that relates the vapor and liquid phase compositions at that pressure, which is the pressure at which this unit is operating. So again, we start by calculating different values of y, vapor phase composition, for some given values of x, the liquid phase composition. So the range is 0 to 1, but you can use any number of data points between 0 to 1. I would say you should use 8 points or so, just to have a smooth plot. So using the equation, we have calculated the values of y for different values of x, and we have now drawn our equilibrium curve. And you always need to draw also your reference line or 45 degrees line, that line. So for this problem, we know the value of the feed composition, and we also know the value of the liquid phase composition leaving the flash is 0.45. So because it's in equilibrium, so that point is obviously on the equilibrium curve. So the question is about finding the vapor phase composition and the fraction of feed that was vaporized. So the vapor phase composition can be obtained very easily just from reading the value here from the graph. So you have this liquid in equilibrium with the vapor, so you're in the equilibrium curve. So that's your value of the and vapor phase composition. Or, I mean, it probably is easier. You can simply use that value of x, 0.45 here, and then just calculate y. So we also need to find f, the fraction that was vaporized. So because we know this point, and we know this other point here. So we have this line, which is the operating line for the flash unit. Then using the equation for the operating line, we can calculate the value of this. Well, we can calculate the value of the slope of this line, and then from the equation of the operating line, the value of f, because we know that the slope of this operating line is, so the term is equal to -1 minus f divided by f. So the slope can be calculated by calculating the change in the y-axis and the change in the x-axis. That's the value of the slope, and the slope is also given by this equation. So that means that you have the value of the slope, so you can calculate the value of f. In this case, just after doing some maths, is 0.68. Question B, go back. For question B, we have batch distillation. Yeah, so we have this batch distillation, so you have some information. So you have a liquid mixture of benzene and toluene. Okay, so initially X1, so the liquid phase is 60% benzene, so X1 is 0.6. So then you do the distillation until the composition of the liquid changes and is now 0.4. So the process is carried out at this pressure, and you have the value of the relative volatility alpha equal to 2.45. So you have to use the Rayleigh equation. To calculate the fraction of the liquid remaining in the liquid. To calculate the fraction of the liquid remaining in the kettle. So how much liquid? Because at the beginning you have some liquid, and then you have some final amount of liquid. You need to find the fraction of the liquid remaining in the kettle and the average composition of the vapor produced. Okay, let me forward. So this is the information that we have. We have the composition of the liquid at the beginning, the composition of the liquid at the end, the relative volatility. So because it says we can use the Rayleigh equation. So this is the Rayleigh equation. So in this equation, We know the value of alpha, we have the value of x1 and x. So we can use the equation to calculate L1 over L. We substitute values, and then we can take the antilog. So L1 over L is equal to 2.62. Or L over L1 is 0.38, which is what we were trying to find, the fraction of liquid remaining. Sorry. Then we want to find the average vapor composition. We can use this equation that it's basically a mole balance. Because the amount of liquid at the beginning times its composition is equal to the amount of liquid at the end times its composition plus the amount of vapor times its composition. So we can assume some value of L1 to calculate L, because they are always changing with this proportion. So it doesn't matter really which value of L1 you use, because L is always going to be 0.38 times L1. So you can give any value, and then you can calculate the amount of vapor that was produced by subtracting the initial amount minus the final amount of liquid. So now that you have L1, X1, L, X, and V, the vapor amount, you can calculate the average composition of the vapor phase that was produced. Okay. So these kind of problems are relatively easy. It all depends on what kind of information you have. So in some cases you have the liquids, maybe the relative volatility. Probably you need to find the liquid phase composition, maybe at the beginning or maybe at the end. It all depends on what kind of information you have. Okay, any questions about distillation? So we have gone through two examples about simple distillation and also distillation with fractionation. Do you have any questions? Nope. Okay, let's do this last problem about this is gas absorption. So the important thing here for gas absorption is to remember that you are using a liquid to remove a component from the gas phase. So the gas phase is leaving the column with a lower concentration because the solute is now in the liquid phase. So the liquid phase is leaving the column with a higher concentration of the solid. Okay. So normally you have some operating parameters. So we have the amount of flow rate of the gas. And in this case, we also have the composition of that gas, which is air. We want to design, or we want to find the height of this gas absorption column in order to reduce the amount of propane in the gas phase to from 1 to 0.4 mole percent. So that's the idea, to have to remove, this component from the gas phase. So we are using a liquid phase. So the liquid phase is some mineral oil. Sorry. So it enters at 1 mole percent. I want to reduce it to 0.5 mole percent. And the liquid, it enters with no solute. There is no propane in the liquid, so it's pure liquid. And then it leaves the column with this concentration, 0.4. So the gas phase, we want to reduce it from 1 mole percent to 0.5 mole percent. And as always, in these kind of problems, we need some relationship, between the gas and the liquid at the equilibrium condition. So in this case, given by this equation, we have some more information about the column, like the cross-sectional area, and so values of the mass transfer coefficient for the gas phase. So overall, we are interested in finding the height of this gas absorption column. So we need to calculate HTU and NTU. And remember, NTU is the term which has some integral in it. So part A says that you have to use the trapezoidal rule, considering 5 equal divisions to calculate this NTU. Okay, so what's the information that we have? You draw a sketch of your gas absorption column. So you always have, your gas phase entering from the bottom and then leaving from the top, the liquid phase entering from the top and leaving from the bottom, because they normally operate in countercurrent mode. So we have values of the compositions of the gas entering and leaving the column. So we have these values. And in this case, we also have the concentrations of the composition of the solute of the liquid phase. So it says that enters pure liquid, so X inlet is equal to 0, and we have the value of the composition of the liquid, leaving the column. So all of these values were obtained from the problem statement. We have the flow rate of the gas, and the mass transfer coefficient, and the cross-sectional area. So again, we need to find height. The height is NTU times HTU. Let's say we can calculate NTU first. So we need to draw our operating lines. Our lines, so we need two lines, the operating line and the equilibrium line. So the operating line is obtained from the values of the compositions at the bottom and at the top of the column. So you have XY values from the top of the column. So those coordinates give you the 2 points for the operating line. And the equilibrium line, for the equilibrium line, you simply use the equilibrium relationship this case, which is y equal to 2 times x. So for the operating line, again, are the 2 points for the at the points for the bottom and top of the column. We have those values from the problem statement. In some cases, the challenging part in solving these kind of problems is to find those values of the compositions, because in some problems, as you saw, during some of the problems in the lectures, sometimes the problem is defined in it could be defined in different ways. For instance, to say that you have some inlet composition of the gas, and you want to remove, let's say, 90% the amount of the solute entering the column. In that case, you have to calculate, okay, if I remove 90% of the amount of solute entering the column, what's the composition, of the column leaving the column. But in this case, in this problem is well, we are not doing that, so all the compositions are given. But you just need to be aware that you can have, those cases. But you always need to find the compositions for both faces at the bottom and at the top, because you need them to draw the operating line. Okay, so with these coordinates, with the bottom and top compositions, you can draw your operating line. So you have those 2 points, and it's very simple to draw, a line. So the other line that you need is the equilibrium line. The equilibrium line, again, is given by the equilibrium relationship, in this case, y equal to 2 times x, because you can give any values of x and calculate y. It's a line, so you only need 2 points. So 1 point is obviously the origin. So when x is equal to 0, y is equal to 0. So if x is equal to 0, y is equal to 0, so that's 1 point. And the other point, it could be, you can use any value of x. But if you notice, I mean, your operating line is only going up to 0.004 in x. So that's basically the limit. That's basically, the maximum value that you need for your equilibrium line in order to perform the rest of the calculation. So yes, in theory, you can give any value of x and to calculate the equilibrium line, but the operating line gives you some kind of, upper value that you can use. So it would be 0.004. So if x is 0.004, then y is 2 times 0.004, which is 0.008. So you have your value of x and your value of y, 0.008. So that gives you the other point of the equilibrium line. So you can draw your nice equilibrium line. So now that you have both lines, the operating line and the equilibrium line, we need to use the graph to basically find the values of y at equilibrium to solve this integral. So what we need to do, so we are trying to solve this integral using the trapezium rule. So you have the formula. So what we need is for values of y, for a given value of y, so for a given value of y, we need to find the value of y equilibrium. Once you have that, you can calculate this part, y minus y at equilibrium. And then we can simply calculate the inverse of that, which is the function that we are trying to evaluate for the integral. This integral is 1 over y minus y at equilibrium. So the value of y, it goes from 0.005. So those are the limits of the integral, which are the two values of the y or gas phase composition. We have the y outlet and y inlet, so the lowest value is 0.005. So we are starting from 0.005 until we reach 0.01, which is the other limit, 0.01, the integral. And we need to different values between 0.005 and 0.01, because the problem says you have to use 5 elements. Let me go back for the integration. 5 equal divisions, the trapezium rule. So that means that the step change is given by the difference of the compositions of the upper limit minus the lower limit divided by 5, the number of elements. So you have increments of 0.001. So you go from 0.005 to 0.01 in increments of 0.001. So 0.005 plus 0.001 is 0.006. The next point would be 0.007, 0.008, and next 0.009, and then 0.01. Yeah. For each of those values of y, we need to find this value of y at equilibrium, and then compute their difference, and then the inverse, and then we use those values to evaluate the function, which is the integral using the trapezium rule. Okay, so we have the value of y. Again, it goes from 0.05 up to 0.1, the limits given by these values of the entering and leaving concentrations of the column. This is the step change. So these are the different values of y. So we need to use the graph to read the values of y at equilibrium. When you look at, for instance, this value 0.006, to get the value of equilibrium, you locate the value of 0.006 y, then you need to draw a line to the operating line, then down to the equilibrium line, and then you read the corresponding value. That's the value of the at equilibrium of y. So for y equal to 0.006, the y at equilibrium is, using your nice graph paper, it will be something around 0.0017. This value. So if you have for y equal to 0.005, so this is this value, of course, 1 point on the operating line, then you just read the corresponding value in the equilibrium line, which is 0, 0. Another point, 0.007, it's this point here in y, and then you draw a line to the operating line, down to the equilibrium line, and you read that value at equilibrium. So it's something around 0.003, as you can see, and so on for all the different values of y. Then you simply calculate that difference, y minus y asterisk, these two variables, and the inverse and those are your function evaluations. So if you remember the trapezium rule, the area under the core is given by delta y over 2, that's the formula, plus the function evaluations. So the extremes are not multiplied by 2, and all the function evaluations in between are multiplied by 2. So all of these, when you add them, they need to be multiplied by 2, these values, but not with the extremes. So delta y is this step change, 0.001 divided by 2, that's the formula, then times the function evaluation, so we have h1, 200, then it will be 2 times the addition of all of these evaluations here in between, plus the value h6, 500. That after doing these operations, it will give that gives you an area of around 1.57. So that means that NTU is that area, which is 1.57. So, well, for the height, we also need to calculate HTU. Remember, HTU is the solid free flow rate divided by the mass transfer coefficient times the cross-sectional area. We have these values from the problem statement. But the solid free flow rate, we need to calculate it. So we have the flow rate with the solid. So if we subtract that that flow rate, if we multiply that flow rate times the subtraction of the flow rate, sorry, of the composition that you have at the entrance, then you can calculate the solid free flow rate. So basically you are removing the amount of solid that you have, in this gas flow rate to give you the solid free flow rate. And then you substitute in the equation, so that gives you HTU, and then the height is simply the multiplication of NTU times HTU. Any questions? No? Okay, part C is about repeating parts A and B, but now using the analytical solution. The analytical solution, or for the analytical solution, you have the equations for NTU. HTU, the equation for HTU is the same. But for NTU, we have already done, the integration for the low solid free case. So NTU is calculated by, sorry, this expression, and this term is given by this. Now the concentrations at equilibrium are simply given by these two relationships, inlet and outlet. So in this case, it's probably easier. So you simply use these relationships to calculate the values of y at equilibrium. So these compositions of the outlet and of the inlet of the liquid phase are given in the problem statement. M is the slope of the equilibrium line. So for this particular problem, I think it was 2 times x, the equilibrium line. So M is, this value of 2. With these equations, then you can calculate these values at equilibrium. And you have the values of the inlet and at the outlet. So you have all the information now to calculate this term. This term, like this. this calculation. And then you substitute example of auto calculated. Then NTU is the difference of the compositions inlet minus outlet divided by value of this term of the logarithm. So NTU is 1.53. In the numerical method, we obtain 1.57. So you can see it's a very close match. Height using this analytical method is 0.15 meters, very close to the value that we use in the numerical method. So in the problem, sorry, in the exam, you will, when you, if there is a question about gas absorption, you will be told about which method to use, either the analytical solution or the graphical solution. And you can also estimate the minimum and optimum flow rates. So remember that for the operating line, for the minimum flow rate is when that operating line touches the equilibrium line. So you have this point of the outlet, and but the other point is when it touches the equilibrium line. So L over V is the related to the slope for that minimum liquid flow rate. So L mean, the minimum flow rate in this case is 10 moles per hour, and the optimum, with the slope for the optimum flow rate for the operating line at optimum flow rate is 1.5 times the value of the equilibrium slope, which was 2. So you multiply 1.5 times 2, which was for the equilibrium line, the slope of the equilibrium line. Then now you have the value of the slope for the optimum. L over V is equal to that slope. So you can get the optimum by multiplying 3 times the gas flow rate. In this case, the optimum flow rate is then 30 moles per hour. Yeah, so you have the minimum flow rate is 10, so at least you need to use 10 moles per hour of the liquid, but the optimum is 30. What's the actual flow rate? So always, it's always L over V, so L over V is equal to the slope, and the slope is the change in Y divided by the change in X. So for our case, the gas flow rate was 10. We have the compositions of the liquid and gas entering and leaving the column. So from there, you can calculate the amount of liquid. So the amount of liquid is 12.5. So at least you need to use 10 moles per hour. So we are using 12.5, so we are above the minimum, which is fine. But the optimum flow rate, following this rule of thumb, we should be using 30. So that means that in theory, we can increase the flow rate 30. If there are other considerations, like probably, there's a cost involved in using a higher flow rate. So maybe it's not possible to reach higher flow rates. Okay, I think you can do question 4 on your own. And if you have any questions, please let me know. All the answers are there. I have actually uploaded more problems. If you want to practice more, it is called Revision Problems 3 on Moodle. Together with the answers. So if you have questions, please let me know. So is that okay? Are you feeling fine for the exam? Excellent. Good to hear that. So again, if you have any questions, please drop me an email or send me a Teams message. I'll be happy to help. Great. So I'm gonna leave it there if you don't have any more questions because I have another revision session in just 10 minutes. So I'll stay here for 3 more minutes in case someone has some particular questions, but if not, all the best in the exam. And as I said again, so please drop me an email if you have questions. Thank you.
Thank you, sir.